Two spacecraft built in the 1970s are at this exact moment traveling through a region of space where the sun's power fades and something far more hostile begins. They have been moving through the darkness for over 45 years and have barely crossed the first of several critical boundaries. What awaits beyond those boundaries is not simply more empty space. It is a radiation-saturated, particle-thin, magnetically alien environment that makes every planet and moon in our solar system look like a protected sanctuary by comparison. The sun has been shielding your planet from a continuous galactic assault for the entire history of life on Earth, an assault of high-energy cosmic rays and interstellar plasma pressing inward from all directions. We cross that boundary together and examine exactly what the instruments actually found waiting on the other side. If you enjoy learning about space and the real science behind it, then a quick like and subscribe really does help this channel. Now, get yourself comfortable, let's begin. Ask most people where our solar system ends, and they will say Neptune. It is a reasonable answer. Neptune is the eighth and outermost of the recognized major planets, orbiting the Sun at an average distance of approximately 30 astronomical units, where 1 astronomical unit equals the average distance between Earth and the Sun, roughly 93 million miles. That number is difficult to hold in the mind. Light, traveling at approximately 186,000 miles per second, takes over 4 hours to cross it. The Voyager 2 spacecraft, launched in 1977 and flung outward through carefully calculated gravity assist maneuvers at Jupiter, Saturn, and Uranus, still needed 12 years of continuous travel to reach Neptune's neighborhood. By any measure built from human experience, Neptune sits at a distance so remote it barely registers as real, and yet it is not the edge, not even close. The solar system does not end at Neptune. It does not end at the Kuiper Belt, the broad, flattened disk of icy objects extending from roughly 30 to approximately 50 astronomical units from the Sun, home to hundreds of thousands of bodies larger than 100 kilometers across, including the dwarf planets Pluto, Eris, Makemake, and Haumea. It does not end at the scattered disk, that dynamically chaotic population of icy objects beyond the Kuiper Belt, whose orbits have been distorted by Neptune's gravitational influence over billions of years into steeply inclined, enormously elongated paths. None of these structures mark the physical limit of the Sun's reach. None of them represent a true boundary between our solar system and what lies beyond it. The boundary of our solar system is defined by something more fundamental, more precise, and dramatically more distant than any planet or belt of icy debris. It is defined by the Sun itself, not as a source of light and gravity, which extend technically without limit across all of space, but as an active, continuously outputting physical object whose influence on the surrounding plasma environment has a measurable, definable outer edge. To understand what that edge is and how it works, you need to understand something that most people who learned about the solar system in a classroom were never told. The Sun does not simply sit in space and shine. Every single second of every single day, it breathes matter into the space around it, and that breath defines our home in a way that nothing else does. The Sun's outer atmosphere is called the corona. It extends millions of kilometers above the visible solar surface. The photosphere and its properties are so extreme they initially seem contradictory. The photosphere, the bright surface of the Sun you see when you look at it through a solar filter, has a temperature of approximately 5,800 Kelvin. As you move upward through the chromosphere and into the corona, the temperature does not decrease as you would expect when moving away from a heat source. It rises dramatically. The corona reaches temperatures exceeding 1 million Kelvin, approximately 170 times hotter than the visible surface directly below it. The precise mechanism responsible for this counterintuitive heating has been one of the central unsolved problems in solar physics for decades. And while leading theories point to the dissipation of magnetohydrodynamic waves propagating upward through the solar atmosphere, the full picture remains an area of active research. What matters for our story is what those extraordinary coronal temperatures produce. At 1 million Kelvin, the thermal energy of individual electrons and protons in the corona exceeds the gravitational binding energy that would otherwise hold them in place close to the Sun. The particles are simply moving too fast for the Sun's gravity to restrain them at that altitude. The result is a continuous, permanent outflow of charged particles, primarily protons and electrons, with smaller contributions from helium ions and trace amounts of heavier elements streaming radially outward from the Sun in all directions at speeds between approximately 250 and 500 miles per second under typical conditions. This outflow is the solar wind. It is not occasional. It is not intermittent. The solar wind has been blowing continuously for the entire 4.5 billion year lifetime of the Sun, and it will continue for approximately another 5 billion years until the Sun exhausts its hydrogen fuel, expands into a red giant, and fundamentally changes its character. Every single second, the Sun's outer atmosphere, the corona expels approximately 1 million tons of charged particles outward into space in all directions. Over the entire history of the solar system, the Sun has lost a total mass roughly equivalent to approximately 1/4 of the mass of Saturn through this continuous outpouring, a tiny fraction of its total mass, but a staggering quantity of material when considered in absolute terms. The solar wind carries with it something even more consequential than matter. It carries the Sun's magnetic field. The corona is a plasma, an electrically conducting gas, and in such a medium, the magnetic field behaves differently than it does in ordinary materials. In a perfectly conducting plasma, the magnetic field lines are effectively frozen into the material. They cannot diffuse through the plasma independently. They must move with it. This principle, called magnetic flux freezing or the ideal magnetohydrodynamic approximation, means that as the solar wind streams outward from the Sun, it drags the Sun's magnetic field along with it, stretching those field lines away from the solar surface and carrying them outward into the surrounding space. Now add the Sun's rotation. The Sun completes approximately one rotation every 25 to 27 days. Depending on latitude, it rotates faster at the equator than at the poles, a consequence of being a gaseous body rather than a solid one. As the solar wind streams outward while the Sun rotates beneath it, the magnetic field lines being carried outward are wound into a large-scale spiral pattern. In the same way that water from a rotating garden sprinkler traces a spiral on the lawn rather than a straight radial line. The result is a structure called the Parker spiral, named for astrophysicist Eugene Parker, who mathematically predicted its existence in 1958, an idea so seemingly audacious at the time that the reviewers of his original submitted paper rejected it as physically impossible, and which was confirmed by direct spacecraft measurement just 4 years later by the Mariner 2 mission en route to Venus. The Parker spiral is not merely a geometric curiosity, it is the magnetic architecture of the entire solar system. Every planet, every moon, every asteroid, every comet, every spacecraft humanity has ever launched exists within this spiraling, magnetized outflow. The solar wind and its embedded magnetic field fill every cubic kilometer of space within an enormous bubble surrounding the Sun, a bubble whose physical properties are fundamentally different from the space outside it. This bubble has a name, the heliosphere. The concept the heliosphere represents is straightforward even if its physics are complex. The Sun is constantly inflating and maintaining a vast region of space filled with its own plasma and its own magnetic field, pressing outward against the surrounding interstellar medium of the galaxy. Everything inside this bubble exists within an environment actively created and maintained by the Sun. Everything outside it exists in a different physical environment, entirely, one governed not by our star but by the collective processes of the galaxy itself. The heliosphere is not a perfect sphere. Its shape responds to the structure of the surrounding interstellar medium and to the Sun's variable output. The side facing the direction of the solar system's motion through the galaxy, called the nose, is compressed by the ram pressure of the interstellar medium flowing past. in the same way that the front of a moving boat compresses the water ahead of it. The trailing side, the tail, or heliotail, extends downstream in the direction away from the solar system's motion, stretched out by the combined effect of the solar wind's outward pressure and the heliosphere's motion through the surrounding medium. Early models predicted an extremely elongated comet-shaped heliosphere with an enormous tail extending perhaps several thousand astronomical units downstream. More recent data from NASA's Interstellar Boundary Explorer satellite, which has been observing the heliospheric boundary remotely from Earth orbit since 2008, suggests the actual shape is more complex, possibly more rounded than the comet model predicted, with magnetic lobes and structural features that early models did not capture. The precise shape of the heliosphere's tail remains an area of ongoing scientific investigation. The heliosphere is also not static. It breathes in rhythm with the Sun's approximately 11-year activity cycle. Every 11 years, the Sun oscillates between a period of relative calm solar minimum, characterized by fewer sunspots, a quieter corona, and a less vigorous solar wind and solar maximum, characterized by intense flaring activity, frequent coronal mass ejections, and a generally denser, faster, more energetically charged solar wind. During solar maximum, the increased outward pressure from the more vigorous solar wind pushes the heliosphere's outer boundary farther from the Sun. During solar minimum, the reduced outward pressure allows the surrounding interstellar medium to compress the heliosphere slightly inward. The boundary of our solar system literally contracts and expands by tens of astronomical units over the course of each solar cycle. The edge of our home is not fixed. It is a dynamic equilibrium that responds to the Sun's heartbeat. As the solar wind travels outward from the Sun, it gradually loses energy. It thins out over the ever-increasing surface area of the expanding sphere it must fill. Its particle density falls with the square of the distance. Its temperature drops, its speed decreases. By the time the solar wind has travelled to the outer solar system somewhere in the range of 75 to approximately 94 astronomical units from the Sun, depending on the direction and the current phase of the solar activity cycle, something physically dramatic happens. The solar wind, which has been travelling outward at supersonic speeds throughout the entire planetary region of the solar system, abruptly slows down. To understand why this is significant, you need to understand what supersonic means in this context. Sound speed in a plasma is not the same as sound speed in air. It is determined by the plasma's temperature, density, and magnetic field strength. The solar wind, for most of its journey from the Sun to the outer solar system, travels faster than the natural wave speed in the medium it is moving through. This is the definition of supersonic flow. When a supersonic flow encounters an obstacle it cannot push through, in this case, the pressure of the surrounding interstellar medium, it cannot gradually slow down and adjust. The information about the obstacle travels at the wave speed of the medium, which is slower than the supersonic flow approaching it. The result is a shock wave, a thin region where the flow transitions abruptly from supersonic to subsonic, and where the kinetic energy of the bulk supersonic flow is converted into heat, magnetic turbulence, and particle acceleration. This standing shock wave in the outer heliosphere is called the termination shock. It is one of the most important boundaries in the solar system, and it sat entirely beyond human direct observation until November of 2004, when NASA's Voyager 1 spacecraft crossed it at approximately 94 astronomical units from the Sun. The data from Voyager 1 at the termination shock were exactly what theory predicted, and the confirmation was enormously satisfying to the scientists who had spent decades waiting for it. The solar wind velocity dropped from approximately 250 miles per second to approximately 80 miles per second, a reduction by a factor of roughly 3 in the thin crossing region. The plasma temperature jumped sharply as the kinetic energy of the bulk flow was converted into thermal energy. The magnetic field became compressed and disordered, its smooth Parker spiral geometry disrupted by the shock's turbulence. The density of the solar wind plasma increased. Every instrument reading was consistent with the signatures of a supersonic to subsonic transition, confirming that Voyager 1 had passed through the termination shock. The asymmetric termination shock distances already established by both spacecraft 94 astronomical units on Voyager 1's side, 84 on Voyager 2's, had confirmed the heliosphere was genuinely asymmetric. That same asymmetry now extended outward through the heliosheath itself. The termination shock is closer to the Sun on one side than the other, reflecting the uneven pressure of the surrounding interstellar medium. The interstellar medium is not pressing equally on all sides of the heliosphere. It has a preferred direction, organized by the local interstellar magnetic field and the flow of the local interstellar cloud relative to the solar system. Our protective bubble is pushed in, slightly but measurably, on the side facing into the interstellar headwind. Beyond the termination shock lies a region that neither spacecraft had ever previously sampled, a zone of turbulent, heated, slowed, magnetically disordered solar plasma that has passed through the shock and is now being redirected by the interstellar medium pressing in from outside. This region is called the heliosheath. It is not a thin transition layer. It is a thick, physically complex buffer zone that both Voyager spacecraft spent years traversing. Voyager 1 crossed the termination shock in 2004 and did not reach the outer boundary of the heliosheath until 2012, 8 years of travel through this intermediate region, covering approximately 30 astronomical units. Voyager 2 crossed the termination shock in 2007 and reached the outer boundary in 2018, 11 years in the heliosheath. Both spacecraft collected invaluable data during these traversals, revealing a region far stranger and more physically complex than pre-mission models had predicted. One of the most striking discoveries in the heliosheath was the behavior of galactic cosmic rays. As Voyager 1 moved outward through the heliosheath toward the outer boundary, its cosmic ray instruments recorded a pattern unlike the smooth, gradual increase that simpler models had anticipated. Instead, the stepwise cosmic ray pattern already established throughout the heliosheath traversal continued toward its conclusion, each layer of magnetic structure providing slightly less shielding than the one before it. The barriers thinning as the heliopause approached. The heliosheath was announcing its own end through the instruments. Simultaneously, the instruments measuring solar energetic particles, the high-energy protons and electrons, accelerated by the Sun's flares and coronal mass ejections and flung outward through the heliosphere, showed a complementary decline. As Voyager 1 approached the outer edge of the heliosheath, solar energetic particle intensities dropped progressively, absorbed and scattered by the magnetic structures of the outer heliosphere before they could reach the spacecraft. These two trends, galactic cosmic rays rising in steps, solar energetic particles falling, were converging toward a dramatic meeting point that both spacecraft would eventually reach. But before describing that meeting point, we need to understand what the heliosphere's architecture is actually protecting against, because most people have never been told, and the answer is genuinely alarming. The space beyond the heliosphere is filled with galactic cosmic rays. These are not a gentle background radiation similar to the natural radioactivity of rocks and soil that living things on Earth have been accustomed to for billions of years. Galactic cosmic rays are individual atomic nuclei that have been accelerated by astrophysical processes to velocities approaching the speed of light. A typical galactic cosmic ray is a proton carrying approximately 1 billion electron volts of kinetic energy. The most extreme examples detected at ground-based observatories carry individual particle energies exceeding 10 to the 20th power electron volts, a quantity that becomes physically comprehensible when expressed as approximately the kinetic energy of a baseball thrown by a professional pitcher, concentrated into a single subatomic particle, moving at a velocity indistinguishable from light speed. These particles originate primarily from supernova remnants distributed throughout the Milky Way. When a massive star exhausts its nuclear fuel and detonates in a core collapse supernova, the expanding shockwave tears through the surrounding interstellar medium at velocities of thousands of miles per second. Charged particles, protons, helium nuclei, The nuclei of heavier elements interact with this shock wave repeatedly, bouncing back and forth across the shock front in a process called diffusive shock acceleration. Each crossing of the shock adds energy to the particle. Over thousands of years of these repeated interactions, a fraction of the particle population accumulates enough energy to escape the shock entirely and stream outward into the broader galaxy. The galactic cosmic ray population, that cumulative product of millions of years of supernova remnant acceleration already described, fills the entire galaxy as an approximately isotropic background flux. The heliosphere does not block galactic cosmic rays completely. What it does is modulate them, reduce their intensity, particularly for lower energy particles, through the scattering and deflecting effect of the tangled Parker spiral magnetic field. A cosmic ray proton trying to travel inward through the heliosphere does not travel in a straight line. The magnetic field forces it to spiral around field lines, scatter off magnetic irregularities, and random walk inward rather than streaming freely. For lower energy cosmic rays, this process is so effective that their intensity inside the heliosphere is significantly reduced compared to the interstellar level. For higher energy particles, whose trajectories are less deflected by the heliospheric field strength, the reduction is smaller. What the Voyager missions directly confirmed is that the intensity of galactic cosmic rays at 1 astronomical unit, the distance from the Sun where Earth orbits, is roughly half of what it is in the interstellar medium. Immediately outside the heliopause, our planet's entire evolutionary history, the development of every living thing that has ever existed on Earth, has occurred inside a magnetic bubble that reduces the cosmic ray background by approximately 50% compared to what the interstellar medium delivers. That is not a trivial difference. Galactic cosmic rays are a significant source of genetic mutation. They penetrate biological tissue, deposit ionizing energy along their tracks through cells, and can damage DNA. A planet receiving twice the galactic cosmic ray flux of Earth over billions of years would face a meaningfully different biological mutation landscape. The heliosphere is not merely interesting astrophysics, it is a component of the conditions under which life here became possible. The heliosphere also deflects the interstellar neutral gas flow. The local interstellar cloud, the specific region of interstellar gas in which our solar system is currently embedded, is moving relative to the Sun at approximately 52,000 miles per hour. Neutral hydrogen and helium atoms from this cloud can penetrate the heliosphere because they are electrically neutral and therefore not deflected by the heliospheric magnetic field. They stream inward freely and have been detected directly by spacecraft instruments, including the Interstellar Boundary Explorer satellite. But the plasma component of the interstellar medium, the ionized portion, which constitutes roughly 20 to 30% of the local interstellar cloud, cannot penetrate the heliopause. The heliospheric magnetic field and the pressure balance at the outer boundary deflect the interstellar plasma around the heliosphere rather than allowing it to flow inward. Without the heliosphere, the inner solar system would be bathed in interstellar plasma of a character fundamentally different from the solar wind environment that has characterized it for 4.5 billion years. All of these protective functions, cosmic ray modulation, interstellar plasma deflection, the provision of a magnetically structured plasma environment, distinct from the broader interstellar medium, emerge from one continuous physical process. The Sun blowing its wind outward and maintaining the pressure balance at the heliosphere's outer boundary. Every day that the Sun continues to output its solar wind, the heliosphere persists. The boundary holds. The protection continues. This has been the case since before the Earth had oceans. The full scale of this protective structure deserves to be stated precisely, because imprecision here obscures something important. The heliosphere, measured to its outer boundary, extends approximately 120 astronomical units from the Sun in the direction of the interstellar headwind, the nose side, and likely farther on the downstream tail side, though the exact extent of the tail remains uncertain. 120 astronomical units equals approximately 11 billion miles. To cross from the Sun to the heliopause at the speed of a commercial airliner, Approximately 560 miles per hour would require approximately 2.2 million years. Light itself, travelling at 186,000 miles per second, takes approximately 16.6 hours to make the crossing. Neptune, the outermost planet, sits at 30 astronomical units. The heliopause is at approximately 120. Everything between Neptune's orbit and the heliopause, a vast annular volume of space containing the Kuiper belt, the scattered disk, and tens of billions of miles of effectively empty solar wind-filled space sits comfortably within the Sun's protective domain. Even the hypothetical Oort cloud, the distant spherical reservoir of comets believed to extend from approximately 2,000 to perhaps 100,000 astronomical units, may have its inner regions partially within or near the heliospheric influence, though the outer Oort cloud is almost certainly beyond any meaningful solar protection. It is worth pausing to recognize how thoroughly this picture overturns the intuitive model of the solar system that most people carry. In the common mental image, the solar system is the planets. Beyond Neptune, there is perhaps a vague awareness of Pluto, and then space becomes foreign territory. The reality is that the solar system, defined by the Sun's physical reach, by the domain of its plasma and magnetic field, extends approximately 4 times farther than Neptune, encompassing a volume of space 800 times larger than the sphere bounded by Neptune's orbit. We live in a solar system whose true size dwarfs what astronomy textbooks typically communicate, and whose protective function extends to distances that no planetary mission has ever been designed to reach. The termination shock at approximately 90 astronomical units marks the first major boundary within this vast domain, the point where the solar wind's supersonic flow gives way to the turbulent, compressed, heated plasma of the heliosheath. The heliosheath itself extends another 30 to 40 astronomical units outward, a thick buffer zone of disordered solar plasma that has passed through the shock and is being gradually turned and mixed by the opposing pressure of the surrounding galaxy. And at the outer edge of the heliosheath, approximately 120 astronomical units from the Sun, lies the boundary that changes everything. The boundary where the Sun's plasma ends and the galaxy's plasma begins. The boundary where the heliosphere terminates and interstellar space commences. The boundary that 2 spacecraft have now crossed and returned, or rather, transmitted data from, the heliopause. Understanding what the Voyager missions found at and beyond that boundary, and what the instruments measured in the moments of crossing, reveals something far more dramatic than any simple description of the boundary can convey. The heliopause is not a gradual fade. It is not a transition region where solar conditions slowly become interstellar conditions over thousands of astronomical units. The spacecraft data shows it to be sharp, physically distinct, and surprisingly thin. On one side, solar plasma, solar magnetic field, the extended domain of a star. On the other side, something categorically different. Something that has never been touched by our Sun. Something that has been filling the spaces between the stars for longer than the solar system has existed. What waits on the other side is not simply more space. It is the galaxy itself, in direct physical contact with our instruments for the first time. And the measurements that both spacecraft made in the moments of and immediately following their crossings tell a story that no description of the heliosphere's interior can fully prepare you for. 8 years is a long time to travel through a single region of space. Voyager 1 crossed the termination shock in approximately 2004, entering the heliosheath, that thick, turbulent buffer zone of slowed, compressed, heated solar plasma that lies between the termination shock and the outer heliospheric boundary. From that moment, its instruments were collecting data from a region no spacecraft had ever previously sampled, transmitting measurements back to Earth across distances so enormous that each signal, travelling at the speed of light, required over 13 hours to arrive. The spacecraft was functioning on computing systems designed in the early 1970s, running on approximately 280 watts of electrical power, generated by decaying plutonium, enough to power a few household light bulbs, and transmitting its data home on a signal of just 22 watts. pointed at Earth by a 3.7-meter dish antenna that was returning data at a rate slower than the dial-up internet connections of the 1990s, and for 8 years, crossing approximately 30 astronomical units of the heliosheath it kept transmitting. What those 8 years of heliosheath data revealed was an environment far more complex than the relatively smooth, gradually weakening solar wind environment of the inner heliosphere. The heliosheath was structured, turbulent, and full of surprises. The solar plasma within it was not simply slow and hot, though it was both of those things. The bulk solar wind velocity having dropped from roughly 300 miles per second before the termination shock to approximately 100 miles per second afterward, and the plasma temperature having jumped sharply at the shock crossing. Within the heliosheath, the plasma was also being continuously redirected. The outward radial flow of the solar wind, which had been the defining motion of the plasma for the entire journey, from the Sun to the termination shock, was gradually being turned by the interstellar medium's pressure. The plasma was being bent deflected from its radial outward path toward a downstream direction, being swept toward the heliotail rather than continuing to press outward symmetrically in all directions. This deflection was not uniform, and the instruments captured its variability in remarkable detail. The magnetic field within the heliosheath showed none of the smooth Parker spiral organization that characterizes the inner heliospheric field. It was disordered, folded back on itself, turbulent at multiple scales simultaneously. The termination shock had randomized the field's direction, and the compression of the outer heliosheath by the surrounding interstellar medium introduced additional structural complexity. The plasma flow within the heliosheath carried magnetic field lines that were being tangled, compressed, and in some regions reconnected, a process in which opposing magnetic field lines break and reconnect in new configurations, releasing stored magnetic energy and accelerating particles in the process. The magnetic foam structures already detected throughout the outer heliosheath, those discrete reconnected magnetic bubbles whose existence no pre-mission model had predicted, continued to influence cosmic ray penetration. During this period, scattering lower energy particles in ways that smooth field models could not accurately replicate. Those models had generally assumed the outer heliosphere would contain a progressively weaker, smoother version of the inner heliospheric field. The reality was more physically interesting and more consequential for the heliosphere's protective function. Magnetic foam provides a different kind of shielding against galactic cosmic ray penetration than a smooth, coherent field does. Cosmic ray particles entering a foamy magnetic environment encounter a complex maze of closed field lines and reconnection boundaries that scatter them in ways that smooth field models cannot accurately predict. Understanding the actual magnetic structure of the outer heliosphere turned out to be essential for accurately modelling how cosmic rays penetrate inward toward the planets. Through all of this, Voyager 1's cosmic ray instruments were tracking the stepwise increase in galactic cosmic ray intensity, described in the previous section, each step corresponding to the spacecraft crossing a boundary between magnetic structures in the heliosheath, each step bringing the measured cosmic ray flux closer to its full interstellar value. And simultaneously, the solar energetic particle instruments continued recording the same progressive decline, the Sun's reach fading instrument reading by instrument reading as the heliopause drew closer. Both trends were approaching their final values simultaneously, the instruments counting down from opposite directions toward the same boundary. The only question was exactly when, and at what distance, the crossing would occur. The answer came in the summer of 2012. In late July and early August of 2012, Voyager 1's instruments recorded a set of changes that, in retrospect, marked the definitive crossing of the heliopause. The galactic cosmic ray intensity, which had been climbing in the characteristic stepwise pattern throughout the heliosheath, made a final sharp jump, not a step like the ones before it, but an abrupt, sustained rise to a new stable level that did not subsequently decrease. Simultaneously, the solar energetic particle flux, which had been declining throughout the heliosheath, dropped to essentially zero. Not to a very low level, not to a reduced level, zero. The sun's energetic particles, which had been detectable throughout the entire journey from Earth to the outer heliosphere, vanished from the instruments. These two changes, the cosmic ray jump and the solar energetic particle disappearance, occurred within approximately 3 days of each other in early August 2012. The convergence was exactly what the theory had predicted. The instruments had been counting down, and they had hit zero simultaneously from opposite directions at the same location in space. But scientists wanted corroboration beyond the particle data before announcing that Voyager 1 had crossed into interstellar space, the expected signature that many had anticipated most strongly, a clear rotation in the direction of the magnetic field. From the solar field's orientation to the interstellar field's orientation did not materialize clearly at the August crossing point. The magnetic field direction did change somewhat at the crossing, but not by the dramatic angle that many models had predicted. This unexpected behavior in the magnetic field created genuine scientific uncertainty about the interpretation of the August 2012 data, and the team spent over a year carefully analyzing what they had measured before publishing their conclusions. The confirmation came from an entirely different type of measurement, one that required waiting for a specific event to occur. The Sun periodically produces large-scale pressure disturbances in the solar wind called global merged interaction regions that form when multiple coronal mass ejections and high-speed solar wind streams merge over time as they travel outward, creating a coherent high-pressure wave that propagates through the heliosphere. Such a wave reached Voyager 1's location in April of 2013. When the wave arrived, it compressed the local plasma and caused it to oscillate at its characteristic resonant frequency, the plasma frequency, which depends directly on the local electron density. Voyager 1's plasma wave instrument detected these oscillations and measured their frequency precisely. The calculation was straightforward. From the measured plasma oscillation frequency, the local electron density could be derived. The result was approximately 80 electrons per cubic centimeter, a value approximately 40 times higher than the electron density, measured by the same technique inside the heliosheath shortly before the crossing. This dramatic density jump was unambiguous. The plasma immediately surrounding Voyager 1 was not thinned out, rarefied solar wind plasma. It was the denser, partially ionized plasma of the local interstellar cloud. Voyager 1 was definitively in interstellar space. The team published their conclusion in the journal Science in September 2013. The crossing had occurred in late August 2012 at a distance of approximately 121.6 astronomical units from the Sun. The heliopause had been crossed. For the first time in history, a human-made object had left the Sun's domain and entered the interstellar medium. 6 years later, Voyager 2 provided a second crossing, and in many ways, a scientifically richer one, because Voyager 2 carried an instrument that Voyager 1 did not, a functioning plasma science instrument capable of directly measuring the solar wind, velocity, temperature, and density in real time. Voyager 1's plasma science instrument had failed in 1980, 37 years before it would have reached the heliopause. The loss was significant. It meant that at the most important moment of the mission, the crossing of the last boundary between the solar system and interstellar space, Voyager 1 could not directly measure the plasma properties on either side of the transition. The electron density measurement from plasma wave oscillations provided crucial information, but it was an indirect technique, available only when a specific type of solar disturbance happened to arrive at the spacecraft's location. Direct plasma measurements at the crossing itself were impossible. Voyager 2 crossed the heliopause on November 5, 2018, at approximately 119 astronomical units. Its plasma science instrument was operational and collecting data throughout the crossing. The results were extraordinary. The solar wind velocity, which had been approximately 95 miles per second in the outer heliosheath just before the crossing, dropped to essentially zero within the heliopause boundary layer. This was not a gradual deceleration spread over tens of astronomical units. The solar wind, the continuous outflow of solar plasma, that had been the defining physical feature of the spacecraft's entire journey from Earth, stopped within a boundary layer estimated to be less than approximately 0.1 astronomical units thick, less than approximately 9 million miles. On one side of that 9 million mile layer, the solar wind was flowing. On the other side, it was absent. The sun's breath ended there, as sharply as if a valve had been closed. The corresponding behavior of the cosmic ray and energetic particle instruments matched Voyager 1's experience precisely. The galactic cosmic ray flux jumped to its full interstellar level. The solar energetic particle flux dropped to 0. Both changes occurred at the same location as the solar wind velocity drop at the same sharp boundary, within the same thin crossing region. 3 independent measurements, 3 independent instrument types, all converging on the same boundary at the same distance. Voyager 2's plasma science instrument also provided the first direct measurement of the temperature of the interstellar plasma immediately outside the heliopause. The interstellar electron temperature in the local interstellar cloud, just beyond the boundary, was measured at approximately 30,000 to 50,000 Kelvin. This number is worth examining carefully because it contains a surprise. The plasma just outside the heliopause in the interstellar medium is actually cooler in terms of individual particle temperatures than the plasma just inside the heliopause in the outer heliosheath. The compressed, shock-heated solar plasma of the heliosheath reaches temperatures approaching 1 million Kelvin. The interstellar plasma outside measures 30,000 to 50,000 Kelvin. Crossing the heliopause outward means moving from hotter individual particles to cooler ones, but into an environment that is nonetheless fundamentally more hostile because the nature of the threat changes entirely from thermal to radiative. Voyager 2's magnetometer provided another crucial measurement: the interstellar magnetic field strength immediately outside the heliopause. The field measured approximately 0.4 nanotesla, enormously weaker than Earth's surface magnetic field of approximately 50,000 nanotesla, and significantly weaker than the solar magnetic field at Earth's orbital distance of approximately 5 nanotesla. To put this in perspective, the interstellar magnetic field threading the local interstellar cloud is roughly 100,000 times weaker than the magnetic field at Earth's surface. It is so weak that human instruments capable of measuring it had to be designed with extraordinary sensitivity, and yet this extraordinarily weak field organizes the flow of interstellar plasma across distances of light years, and channels the propagation of galactic cosmic rays across the entire local galactic neighborhood. The magnetometer data also revealed something physically intriguing about the heliopause itself. The interstellar magnetic field direction measured just outside the heliopause, pointing approximately toward the galactic plane, differed only slightly from the direction of the solar magnetic field measured just inside, in the outer heliosheath. This small difference explained why the magnetic field rotation at the heliopause had been less dramatic than many pre-mission models predicted. The interstellar magnetic field in the local interstellar cloud is roughly aligned with the heliospheric field at the crossing point, rather than being oriented at a large angle to it. This alignment is not coincidental. The interstellar magnetic field partially controls the orientation of the heliosphere itself, contributing to the pressure that shapes the heliopause and influencing the direction in which the heliospheric current sheet, the vast, wavy surface separating regions of opposite solar magnetic polarity within the heliosphere, is oriented. The heliospheric current sheet deserves a brief explanation because it is one of the solar system's most remarkable structural features, and one whose effects extend all the way to the heliopause. The Sun's magnetic field has 2 hemispheres of opposite polarity, a north magnetic hemisphere and a south magnetic hemisphere, analogous in a very rough sense to the north and south poles of a bar magnet, though the solar field is far more complex. The boundary between these 2 hemispheres, carried outward by the solar wind, forms a vast undulating surface called the heliospheric current sheet. Because the Sun's magnetic axis is tilted relative to its rotation axis, the current sheet is not flat, it is warped into a wavy, rippled surface that rotates with the Sun, creating a structure that has been described visually as resembling a ballerina's spinning skirt. The current sheet extends throughout the entire heliosphere, and spacecraft crossing it repeatedly as the Sun rotates detect alternating sectors of inward and outward magnetic field polarity. In the outer heliosheath, the current sheet becomes compressed by the surrounding interstellar pressure, contributing to the magnetic complexity that both Voyager spacecraft detected in that region. Near the heliopause, the current sheet is further distorted by the interaction with the interstellar magnetic field draping around the heliosphere's outer boundary. The interplay between the heliospheric current sheet and the interstellar field at the heliopause contributes to the structural details of the crossing, including the thin boundary layer of anomalously high plasma temperature that Voyager 2 detected just inside the heliopause during its crossing. That anomalous boundary layer, a thin zone of extremely high plasma temperature detected by Voyager 2 between the outer heliosheath and the heliopause proper, was one of the most scientifically intriguing discoveries of the crossing. In the crossing data, the instruments detected a region roughly 0.3 astronomical units thick just inside the heliopause, where the plasma temperature was dramatically higher than either the general heliosheath temperature or the interstellar temperature outside. This localized heating is consistent with theoretical predictions of intense magnetic reconnection occurring at the heliopause boundary, a process in which the solar magnetic field and the interstellar magnetic field, pressed together at the contact surface, break and reconnect in new configurations, releasing stored magnetic energy that heats the local plasma. The heliopause is not simply a passive pressure balance surface. It is an active site of magnetic interaction between the Sun's magnetic domain and the galaxies. Both crossings, Voyager 1 in 2012, Voyager 2 in 2018, also confirmed something important about the geometry of the heliopause relative to the termination shock. Voyager 1 crossed the termination shock at approximately 94 astronomical units, and the heliopause at approximately 121 astronomical units, a heliosheath thickness of approximately 27 astronomical units on that side of the heliosphere. Voyager 2 crossed the termination shock at approximately 84 astronomical units, and the heliopause at approximately 119 astronomical units, a heliosheath thickness of approximately 35 astronomical units on its side. The heliosheath is not the same thickness in all directions. It is thinner on the nose side, the side facing into the interstellar headwind, where the interstellar medium's ram pressure compresses the heliosheath most effectively, and thicker on the flanks and tail side where the pressure is lower. The asymmetry extends through every layer of the heliosphere, from the termination shock inward to the heliopause outward. Voyager 1 is currently travelling in the general direction of the constellation Ophiuchus, roughly toward the nose side of the heliosphere, the upstream direction of the interstellar wind. Voyager 2 is travelling in a direction roughly toward the southern hemisphere of the heliosphere, at a substantial angle from Voyager 1's path. The fact that two spacecraft travelling in significantly different directions both cross the heliopause at distances within a few astronomical units of each other provides confidence that the heliopause is a roughly consistent boundary in terms of distance, even accounting for the measured asymmetry. The heliosphere does not have a dramatically thin side and a dramatically thick side. It has a modestly compressed nose and a modestly extended tail, and both Voyager crossings sampled the mid-latitude flanks of this overall structure at distances that are broadly representative of the heliopause's general location. After crossing the heliopause, both spacecraft continued transmitting data. Voyager 1, as of the time of writing, is at approximately 160 astronomical units from the Sun, 40 astronomical units beyond the heliopause, measuring properties of the local interstellar medium at the greatest distance from Earth ever achieved by any human technology. Voyager 2 is at approximately 130 astronomical units, approximately 10 to 15 astronomical units, beyond its heliopause crossing point, sampling the interstellar medium at a different location and different direction than Voyager 1. The data both spacecraft have returned from beyond the heliopause has been consistent and mutually confirming. Galactic cosmic ray fluxes are stable at their elevated interstellar levels. Solar energetic particles are absent. The solar wind is undetectable as a bulk flow. The plasma properties match those of the local interstellar cloud within measurement uncertainties. The magnetic field is weak, stable, and organized by interstellar rather than solar processes. Neither spacecraft has detected any evidence of a bow shock, a shock wave that some models predicted would form upstream of the heliosphere, where the interstellar wind rams into it. The absence of a detectable bow shock suggests that the interstellar medium in our immediate neighborhood is moving relative to the solar system too slowly to create a supersonic shock upstream of the heliopause, though the question remains partially open as measurements continue. What the heliopause crossing data from both Voyager missions reveals, taken together, is a boundary that is real, sharp, physically distinct, and thinner than many pre-mission models anticipated. The transition from heliospheric plasma to interstellar plasma occurs within a boundary layer of only a few tenths of an astronomical unit, a few tens of millions of miles. At Voyager speeds, both spacecraft cross this layer in a matter of days to weeks. On one side, the Sun's plasma, the Sun's magnetic field, elevated solar energetic particle intensities, reduced galactic cosmic ray flux. On the other side, interstellar plasma, interstellar magnetic field, zero solar energetic particles, full galactic cosmic ray intensity. The boundary is not gradual, it is a wall, and once crossed, there is no ambiguity about which side you are on. This sharpness matters for several reasons beyond its intrinsic scientific interest. It means that the heliosphere's protective function does not fade gradually over tens or hundreds of astronomical units. It ends. A spacecraft at 120 astronomical units is inside the heliosphere and enjoys all the protections that implies. A spacecraft at 121 astronomical units is in the interstellar medium and is exposed to the full galactic cosmic ray background, the full interstellar plasma environment, and the complete absence of solar energetic particle input. The transition between these two states happens within approximately 9 million miles a distance that light crosses in approximately 48 seconds. The universe has a sharp edge here, and both Voyager spacecraft have confirmed exactly where it sits. For any future mission designed to operate beyond the heliopause, whether a dedicated interstellar probe carrying more advanced instruments than the Voyager spacecraft, a generation ship intended for eventual stellar transit, or any other object meant to function in the interstellar medium, the heliopause crossing defines a fundamental mission phase transition. Before crossing, operating in a heliospheric environment with familiar properties shaped by decades of spacecraft observations. After crossing, operating in an environment whose properties are characterized only by the limited data returned by two aging spacecraft and by remote sensing observations that cannot replace in situ measurement. The interstellar medium immediately beyond the heliopause is the least directly characterized environment that human technology has ever encountered, and the measurements that define it come from instruments that were never designed to survive this long or travel this far. Both Voyager spacecraft are losing power. Each radioisotope thermoelectric generator loses approximately 4 watts of electrical output per year as the plutonium-238 fuel decays. Both spacecraft have already shut down multiple instruments to conserve power for the instruments considered most scientifically valuable in their current environment. Voyager 1 has turned off its camera system, its ultraviolet spectrometer, and its low-energy charged particle instrument, among others. Voyager 2 has made similar power conservation decisions. The mission teams estimate that one or both spacecraft may lose the ability to power their remaining instruments sometime around the late 2020s or early 2030s, ending the data return from the only human-made objects that have directly sampled the interstellar medium. When those transmissions finally cease, humanity will lose its only in-situ sensors beyond the heliopause. The interstellar medium will return to being characterized entirely by remote observation, spectroscopy of starlight absorption, energetic neutral atom imaging from Earth orbit, theoretical modelling constrained by the Voyager data. The direct measurement window opened by the Voyager missions will close, and what will remain is a set of irreplaceable measurements from two specific locations and two specific trajectories through the immediate heliospheric vicinity, a data set that will be analysed and reanalyzed for decades, but that cannot be expanded without a new mission. The physical environment those measurements have revealed, the interstellar medium of the local interstellar cloud in the immediate vicinity of the heliosphere, is the subject of what comes next, because understanding what the heliopause separates our solar system from requires characterizing the interstellar medium not just as measured by the brief Voyager crossings, but as an extended environment with specific, quantifiable properties that make it fundamentally different from anything inside the heliosphere. The particle density, the radiation field, the magnetic structure, the temperature, the absence of anything resembling solar protection. The interstellar medium is not simply space with the solar wind removed. It is a different physical regime, governed by different dominant processes, presenting different challenges to any unprotected object within it. And understanding those challenges in precise physical terms, not in vague descriptions of darkness or emptiness, but in actual measured quantities with actual physical consequences, is what reveals why the boundary both Voyager spacecraft crossed represents something more than a line on an astronomical chart. It represents the edge of the only cosmic environment in which life on this planet has ever existed. The word environment implies something habitable. A forest is an environment. A coral reef is an environment. Even the surface of Mars, barren, irradiated, bitterly cold, with an atmosphere too thin to breathe and soil chemistry toxic to unprotected biology, qualifies as an environment in the sense that it has a definable set of physical properties that a sufficiently robust piece of engineering could, in principle, be designed to survive within. The interstellar medium beyond the heliopause challenges even this expansive definition. It is not simply hostile in the way that planetary surfaces and deep space within the heliosphere are hostile. It is hostile in kind, a physically distinct regime governed by processes that have no meaningful analogue within the solar system, presenting challenges that no spacecraft has yet been engineered to address, and that no biological organism has ever encountered and survived. To understand precisely why, the dramatic boundary crossings must give way to the actual measured physical properties of the environment the Voyager spacecraft entered, because the numbers are where the true hostility lies, not vague descriptions, not poetic language about the void, actual numbers, actual densities, actual radiation levels, actual magnetic field structures, because the numbers are where the true hostility lives, and the numbers are more extreme than most descriptions of interstellar space convey. Begin with the structure of where we are. Our solar system currently sits inside a specific, named region of the interstellar medium called the local interstellar cloud, sometimes referred to informally as the local fluff, a name that feels almost comically inadequate once you understand what it actually contains. The local interstellar cloud is a region of partially ionized interstellar gas, approximately 30 light-years in its longest dimension, and roughly 17 light-years across in the shorter direction. It is not spherical. It is irregular, with a somewhat elongated and lumpy shape reflecting the chaotic processes that created and continue to shape it. The solar system entered this cloud somewhere between 45,000 and approximately 150,000 years ago. The uncertainty in that estimate reflecting how difficult it is to precisely reconstruct the solar system's trajectory through local interstellar structures over tens of thousands of years. The local interstellar cloud is itself embedded within a much larger structure called the local bubble. The local bubble is a cavity in the broader interstellar medium of the Milky Way, an irregularly shaped region of dramatically lower than average interstellar density that extends approximately 300 light-years in its shorter dimension and perhaps 1,000 light-years or more in its longest extent. The cavity is ancient. It was excavated by a series of supernova explosions from massive stars that passed through this region of the galaxy over the past approximately 10 to 20 million years. Current models suggest that somewhere between 14 and 20 individual supernova events contributed to carving the local bubble to its current dimensions, each explosion sweeping outward through the surrounding interstellar medium and driving the denser gas ahead of the blast wave. Over millions of years, these successive explosions cleared most of the denser cold and warm neutral gas from the region, leaving behind a hot, diffuse cavity filled with plasma at temperatures of approximately 1 million Kelvin. The walls of the local bubble are where that swept-out material accumulated. Compressed into shells and sheets of denser interstellar gas, the walls mark the transition back to more typical galactic interstellar medium densities. Several of the most prominent nearby star-forming regions, including portions of the Scorpius-Centaurus-OB association, the nearest region of recent massive star formation to the solar system, at roughly 400 light-years, are located in or near the walls of the local bubble, where the compressed material has subsequently become dense enough to collapse gravitationally and form new stars. The supernova explosions that created the local bubble seeded future stellar generations in the same act that destroyed the prior interstellar structure. Within this cavity floats the local interstellar cloud, a denser patch of partially ionized gas that has survived within the local bubble interior without being entirely dispersed by the hot surrounding plasma. The cloud is warmer and less dense than the cold neutral medium that dominates galactic interstellar space in denser regions, but it is orders of magnitude denser than the hot million Kelvin plasma filling the broader local bubble. It occupies an intermediate position in the interstellar medium's temperature density phase structure, what astronomers classify as the warm partially ionized medium, and it represents the immediate physical context of our solar system's journey through the galaxy. Now, the numbers. The particle density of the local interstellar cloud is approximately 0.3 hydrogen atoms per cubic centimeter. This is the density of the medium that Voyager 1 and Voyager 2 are currently moving through, the medium that presses against the heliopause from outside, the medium into which any future interstellar mission would be launched. 0.3 atoms per cubic centimeter. To translate this into something comprehensible, consider that the air surrounding you at sea level contains approximately 2.7 times 10 to the 19th molecules per cubic centimeter. That is 27 million trillion molecules in every cubic centimeter of the atmosphere you are breathing. The local interstellar cloud contains 0.3 of a single atom per cubic centimeter. The ratio between these two densities is approximately 9 times 10 to the 19th, roughly 100 billion. The interstellar medium is not merely thin or vacuous in the way that the space between planets is thin and vacuous. It is so incomprehensibly empty that no everyday experience, no laboratory experiment, no engineering process available to current human technology can produce a comparable vacuum. The best laboratory ultra-high vacuum systems achieve approximately 10 to the 7th molecules per cubic centimeter, still tens of millions of times denser than the local interstellar cloud. When physicists and engineers speak of ultra-high vacuum as an extraordinary achievement requiring specialized chambers, ion pumps, and baking procedures to eliminate outgassed molecules from chamber walls, they are describing a density that remains fantastically crowded by comparison to the interstellar medium. The space between the stars is not a vacuum in any sense that the word carries within the context of human experience. It is something for which there is genuinely no terrestrial reference point, but the local interstellar cloud is not the least dense interstellar environment in our immediate neighborhood. The hot plasma filling the broader local bubble interior, the plasma left behind by those ancient supernova explosions, has a density of approximately 5 times 10 to the negative 3 particles per cubic centimeter. This is roughly 60 times less dense than the local interstellar cloud. The local bubble interior represents the most rarefied environment directly accessible to spacecraft launched from our solar system. Should any mission travel far enough to exit the local interstellar cloud before encountering the next distinct interstellar structure, An object moving through the local bubble interior beyond the local interstellar cloud would find itself in an environment with individual particle temperatures exceeding 1 million Kelvin, but a total particle density so low that the thermal energy content per unit volume, which depends on both temperature and density, remains extraordinarily small, hot but nearly empty, in the counterintuitive way that only extreme plasma physics can produce. The temperature structure of the local interstellar cloud itself is worth examining precisely because it defies intuitive expectations in its own right. The bulk gas temperature of the cloud is approximately 6,000 to 8,000 Kelvin, significantly hotter than the surface of many red dwarf stars, which have photospheric temperatures in the range of 3,000 to 4,000 Kelvin. Yet nothing in the local interstellar cloud burns or glows visibly in the way that a stellar surface does, because the density is so low that the total thermal energy content per unit volume is negligible. Temperature in a plasma is a measure of the average kinetic energy of individual particles. When there are only 3/10 of a particle per cubic centimetre, the aggregate thermal energy of those particles is essentially zero even if each individual particle is moving quickly. The interstellar medium can be simultaneously hot in the thermodynamic sense and cold in any practical engineering sense, a combination that has no everyday analogue. Approximately 20 to 30% of the hydrogen in the local interstellar cloud is ionized, stripped of its single electron by ultraviolet radiation from nearby hot stars, including the hot white dwarf companion of Sirius, approximately 8.6 light-years away, whose ultraviolet output contributes significantly to the local interstellar radiation field. The remaining 70 to 80% consists of neutral hydrogen atoms. The cloud also contains helium at approximately cosmic abundance ratios, roughly 10 hydrogen atoms for every helium atom, along with trace quantities of heavier elements, including carbon, oxygen, nitrogen, neon, magnesium, silicon, sulfur, and iron. Many of these heavier elements are significantly depleted relative to solar photospheric abundances because a fraction of each element has condensed onto the surfaces of interstellar dust grains rather than remaining in the gas phase. Those dust grains constitute a physically important component of the interstellar medium that is easy to underestimate. Interstellar dust particles are extraordinarily small, ranging from a few nanometers to roughly 1/10 of a micrometer in size, and extraordinarily sparse by terrestrial standards. But they have measurable effects on light propagation across light-year distances and contribute meaningfully to the interstellar medium's overall physical character. Dust grains in the warm, partially ionized medium of the local interstellar cloud are composed primarily of silicate minerals and carbonaceous materials, with compositions broadly similar to the mineral compositions of meteorites and rocky planets. Some grains carry ice mantles in colder interstellar regions, though in the warm local interstellar cloud, ice mantles are less stable. The significance of interstellar dust for any spacecraft operating in the interstellar medium is primarily mechanical rather than chemical. A dust grain, 1/10 of a micrometer, across travelling at the relative velocity between the solar system and the local interstellar cloud, approximately 52,000 miles per hour, carries kinetic energy, proportional to its mass and velocity squared. Individual grains at this size have masses so small that the kinetic energy of any single impact is negligible. But a spacecraft travelling through the interstellar medium at a significant fraction of the speed of light as any mission designed to reach even the nearest stars within a human lifetime would need to encounter the dust. Grains at velocities millions of times higher than the current relative velocity between the solar system and the interstellar medium. At 20% of light speed, which is the target velocity for the breakthrough starshot laser sail concept, even a grain, 1/100th of a micrometer across, carries enough kinetic energy to penetrate a thin sail material or damage a millimeter-scale electronic component. The dust density of the interstellar medium, negligible at solar system traversal speeds, becomes a significant engineering constraint at relativistic velocities. The galactic cosmic ray environment of the interstellar medium beyond the heliopause demands extended treatment because it represents the most biologically and electronically significant hazard facing any unprotected object in this people's environment. The basics of cosmic ray origin were established in the previous section. Galactic cosmic rays are atomic nuclei accelerated to near-light velocities by supernova remnants and other astrophysical accelerators distributed throughout the Milky Way, filling the galaxy with an approximately isotropic background of energetic particles. What deserves more precise characterization here is the specific nature of that background, its energy spectrum, its composition, its intensity, and its practical consequences. The galactic cosmic ray energy spectrum spans an enormous range, from approximately 100 million electron volts at the low end, through approximately 10 to the 20th power electron volts at the most extreme end. This range covers a factor of roughly 1 trillion in particle energy. The spectrum is not flat, it follows a power law, meaning there are vastly more lower energy cosmic rays than higher energy ones. For every factor of 10 increase in energy, the number of cosmic rays at that energy decreases by approximately a factor of 100 to 1000, depending on the energy range. This means that the overwhelming majority of galactic cosmic ray interactions with matter involve particles at energies between approximately 100 million and approximately 10 billion electron volts. These are the particles that the heliosphere most effectively modulates, and they represent the dominant radiation hazard for any unprotected object making the crossing. The composition of galactic cosmic rays mirrors the elemental composition of the galaxy in a modified form. Approximately 89% are protons, hydrogen nuclei. Approximately 10% are alpha particles, helium nuclei. The remaining approximately 1% consists of heavier nuclei, carbon, oxygen, nitrogen, neon, magnesium, silicon, iron, and every other element in the periodic table. There are also electrons and positrons at lower abundances. The relative abundances of different elements in cosmic rays carry information about both the source environments, the stellar interiors, and supernova ejecta, where the atoms originated, and the propagation history through the galactic magnetic field. Since different elements are produced at different rates in different types of nuclear burning and supernova explosions, for any biological organism exposed to the full interstellar cosmic ray flux, the consequences are severe. The most biologically damaging cosmic ray interactions are not the direct passages of primary cosmic ray nuclei through tissue. These are energetic enough that they typically pass through without depositing all of their energy, leaving a trail of ionization damage along their track, but not stopping entirely within the body. More damaging are the secondary particle showers produced when primary cosmic rays collide with atomic nuclei in tissue or shielding material. A high-energy cosmic ray proton striking an atomic nucleus in human tissue produces a spray of secondary particles, neutrons, pions, gamma rays, lighter nuclei that radiate outward from the interaction point in a cone of ionizing radiation. This secondary shower can deposit far more energy locally than the primary particle would have deposited on its own. The dose rate from galactic cosmic rays in the interstellar medium immediately beyond the heliopause is significantly higher than the dose rate experienced anywhere within the heliosphere. Mars-bound astronauts who must travel through space with only their spacecraft structure for shielding already face projected galactic cosmic ray doses that approach or exceed established lifetime career limits for NASA astronauts on missions of 2 to 3 years duration. The dose rate in interstellar space beyond the heliopause, where the heliospheric modulation that partially reduces the cosmic ray flux is absent, would be meaningfully higher still. For missions lasting years or decades in the interstellar medium, galactic cosmic rays represent a fundamental constraint on crew survival that cannot be addressed through any passive shielding approach that adds acceptable mass to a spacecraft. The only effective mitigation for the highest energy cosmic rays is active magnetic shielding, generating an artificial magnetic field around the spacecraft, large and strong enough to deflect incoming cosmic rays. The engineering requirements for such a system at scales sufficient to protect a crewed vehicle are currently far beyond available technology. For the Voyager spacecraft themselves, The cosmic ray environment beyond the heliopause creates challenges to electronics longevity through the single event effects mechanism. When a cosmic ray passes through an integrated circuit, it deposits ionizing energy along its track. If that track passes through a transistor gate or a memory cell, it can flip a stored bit, corrupt a processor register, or in extreme cases trigger a latch-up condition that permanently damages a circuit element. The Voyager spacecraft were designed in the early 1970s using semiconductor components with feature sizes measured in micrometers, relatively large by modern standards, and correspondingly more robust against single event effects because the sensitive volumes within each transistor are larger and thus present a larger target. Modern integrated circuits, with transistors measured in nanometers, pack billions of transistors into areas where the Voyager chips contain thousands, making each individual transistor a far smaller and harder to hit target in absolute terms, but making the overall chip far more susceptible because any given cosmic ray track through the chip will pass through many more individual transistors. This presents a fundamental design challenge for any future interstellar probe. A spacecraft designed to operate for decades in the interstellar cosmic ray environment must use radiation-hardened electronics whose component feature sizes are large enough to resist single event effects but larger. Feature sizes mean lower performance, higher power consumption, and heavier components. Every gram of additional electronics mass is a gram that must be accelerated to the spacecraft's operating velocity, which at the extreme velocities required for meaningful interstellar transit demands enormous additional propulsive energy. The cosmic ray environment imposes a direct trade-off between electronics reliability and mission performance that has no satisfying resolution with current technology. The interstellar magnetic field adds further complexity to any operational picture of the environment beyond the heliopause. The interstellar magnetic field measured directly at the heliopause crossing threads the entire local interstellar cloud on scales of tens of light years. This field did not form suddenly or locally. It is a remnant and amplification product of processes operating at galactic scales, the differential rotation of the Milky Way, which stretches and wins magnetic field lines over millions of years, the turbulent energy injection by supernova explosions, which randomizes and amplifies magnetic fields on intermediate scales, and smaller-scale magnetohydrodynamic turbulence within individual interstellar clouds, which cascades magnetic energy from large scales to small scales in a process analogous to turbulent energy cascades in ordinary fluids. The direction of the local interstellar magnetic field pointing approximately toward the galactic plane, as inferred from both the Voyager magnetometer data and the IBEX energetic neutral atom ribbon observations, reflects the large-scale organization imposed by the Milky Way's differential rotation. The galactic magnetic field has a preferred direction aligned roughly parallel to the galactic plane and following the spiral arm structure of the galaxy. Local perturbations from supernova explosions and the dynamics of individual interstellar clouds distort this preferred direction regionally, but over scales of hundreds of light years the field tends to return to its large-scale organized direction. For a spacecraft navigating through the interstellar medium, the magnetic field is relevant primarily through its effect on galactic cosmic ray trajectories. Charged particles moving through a magnetic field are deflected perpendicular to both their velocity and the field direction. The degree of deflection depends on the particle's charge, its momentum, and the field strength. For the weak interstellar magnetic field of the local interstellar cloud, the deflection radius, the radius of the curved path, a cosmic ray follows in the field for a typical 1 billion electron-volt proton, is approximately 1 astronomical unit. This means that typical interstellar cosmic rays are deflected by the local magnetic field on scales comparable to the size of planetary orbits. The cosmic ray background in interstellar space is not perfectly isotropic. It has directional structure imposed by the local magnetic field geometry and by the locations of nearby cosmic ray sources, but the anisotropy at the energies relevant for biological and electronic effects is small enough that it does not change the fundamental character of the radiation hazard. One of the most practically significant aspects of operating beyond the heliopause is not the particle environment, but the communication environment. Both Voyager spacecraft transmit at frequencies in the X-band of the radio spectrum, approximately 8 GHz for Voyager 1. At the spacecraft's current distance of approximately 160 astronomical units, the signal arrives at Earth with a power of approximately 10 to the negative 26th watts. This is a number so small that writing it out provides no intuitive sense of its magnitude. The Deep Space Network receiving dishes, the largest radio telescopes operated by NASA, with diameters up to 70 meters, must integrate signal for extended periods and use sophisticated noise reduction techniques to extract usable data from this power level. The one-way light travel time from Voyager 1 at 160 astronomical units is approximately 22 hours. Every command sent from Earth takes 22 hours to arrive at the spacecraft, and every response takes 22 hours to return. Total round-trip communication delay, 44 hours. For Voyager 2, at approximately 130 astronomical units, the one-way delay is approximately 18 hours. For a spacecraft at the distance of the heliopause, approximately 120 astronomical units, the one-way light travel time is approximately 16.5 hours. For a spacecraft at 1,000 astronomical units still within the inner regions of the hypothetical Oort cloud, nowhere near the nearest stars, the one-way delay exceeds 5 days. Any meaningful interstellar probe designed to operate beyond the solar system would need to function autonomously for essentially its entire mission. Commands from Earth cannot arrive in time to respond to rapidly evolving situations. Fault protection, science operations, navigation corrections, instrument management, all of these must be handled by onboard systems without human intervention. This requires a level of spacecraft autonomy that exceeds anything currently deployed in operational deep space missions. The Voyager spacecraft carry relatively simple fault protection logic by modern standards, and they have experienced numerous anomalies over their 40-plus years of operation that have required rapid response from Earth-based teams. At interstellar distances, that response time becomes irrelevant. The spacecraft must solve its own problems or fail. Navigation in the interstellar medium presents a related challenge. Within the solar system, spacecraft are navigated using a combination of radio signal timing and Doppler measurements. The Deep Space Network transmits a signal to the spacecraft retransmits it, and the round-trip time and frequency shift precisely determine the spacecraft's position and velocity relative to Earth. This technique works extremely well within the heliosphere, because the solar gravitational field provides a well-characterized dynamical background against which positions and velocities can be computed with high accuracy. Beyond the heliopause, the same technique continues to work. Both Voyager spacecraft are navigated this way, but it provides only the spacecraft's position relative to the solar system's center of mass. Navigating relative to a target star system, which any interstellar mission would eventually need to do, requires both extremely precise knowledge of the target star's position and proper motion over decades, and a navigation framework that accounts for the effects of the interstellar medium on the spacecraft's trajectory. The interstellar medium exerts very small but non-zero forces on a traveling spacecraft through the ram pressure of the interstellar gas and the magnetic pressure of the interstellar field. At Voyager speeds, these effects are negligible. The spacecraft is moving at approximately 38,000 miles per hour, which is slower than the thermal speed of the interstellar plasma particles and far below the velocities at which ram pressure effects become significant. At the relativistic velocities contemplated for rapid interstellar transit, however, the ram pressure of even the extraordinarily thin interstellar medium becomes a meaningful deceleration force. A spacecraft moving at 20% of light speed, approximately 134 million miles per hour, encounters the interstellar medium's 0.3 particles per cubic centimeter with a ram, pressure sufficient to cause measurable deceleration over distances of light years. The cumulative physical picture of the interstellar medium beyond the heliopause can now be assembled from these individual characterizations into a coherent portrait of the environment. It is a near-perfect vacuum by any human engineering standard, containing the same warm, partially ionized gas of the local interstellar cloud, at its characteristic near-vacuum density, threaded by a magnetic field of approximately 0.4 nanotesla, pervaded by a continuous flux of galactic cosmic rays whose intensity is approximately double the value modulated to by the heliosphere, and dusted with nanometer to submicrometer silicate and carbonaceous particles at densities that are negligible at low speeds, but potentially significant at relativistic velocities. Communication across it is subject to speed of light delays measured in years for the nearest stars and decades for even the closest stellar neighbours. Navigation within it requires autonomous onboard systems of a sophistication not yet demonstrated in operational spacecraft. Radiation shielding within it requires either accepting dose rates that exceed current human spaceflight limits, or developing active magnetic shielding technology of a mass and complexity not yet achievable. None of this is speculation. These are the measured properties of the specific interstellar environment into which our solar system is currently embedded, derived from spacecraft data, astronomical spectroscopy, and energetic particle observations that have been peer-reviewed, replicated, and refined over decades. The interstellar medium is not the unknown. It is the measured, and the measurement reveals an environment that makes the inner solar system, even the surfaces of airless rocky bodies like the Moon and Mercury, look like sheltered, protected, survivable places by comparison. All of this characterization applies to the immediate vicinity of the heliosphere, the local interstellar cloud, and the inner regions of the local bubble within the first few tens of light years of our solar system's neighborhood. At the distance of the nearest stellar systems at 4.24 light-years for Proxima Centauri, the properties of the interstellar medium are broadly similar to those in our immediate vicinity, since we and the nearest stars share the same local interstellar cloud. But the stars themselves introduce new hazards, new dynamics, new environments within their own stellar systems that are distinct from the interstellar medium between them. Understanding those distances not just as numbers but as physical realities, as barriers, as measurements of the true scale of the isolation that the interstellar medium imposes on stellar systems, is the final and most important step in grasping what it means to leave the solar system behind. 4.24 light-years. That is the distance to Proxima Centauri, the nearest known star to our solar system, 4.24 light-years. The number is small enough to fit in a sentence, precise enough to feel scientific, and completely, utterly meaningless to any human brain, attempting to hold it as a physical reality rather than an abstract quantity. Every number used in astronomy suffers from this problem. To some degree, astronomical distances are so far outside the range of distances that human evolution equipped us to process that even the most careful attempts at translation fall short. But the distance to the nearest star deserves a sustained attempt at translation, because it is the most important number in understanding what interstellar space actually is, and why the boundary we have spent 3 parts of this story characterizing represents something far more profound than a line on an astronomical chart. 1 light-year is the distance light travels in 1 year. Light travels at approximately 186,000 miles per second. In 1 minute, light covers approximately 11 million miles. In 1 hour, approximately 670 million miles. In 1 day, approximately 16 billion miles. In 1 year, 365 days, approximately 315 million seconds, light covers approximately 5.88 trillion miles. 4.24 light-years is therefore approximately 24.9 trillion miles. Written out in full, that number is 24 million miles. 24 followed by 12 zeros, expressed in miles. These kinds of number translations are common in astronomy writing, and they typically produce a brief cognitive jolt before the brain reasserts its inability to process the quantity and moves on. So instead of stopping at the number, Follow it through to its practical consequences. Consider what it means for the only human-made objects that have actually entered interstellar space. Voyager 1 is currently traveling at approximately 38,000 miles per hour. This velocity was not achieved easily. It required the most powerful rockets of its era, combined with the gravity assist trajectory already described, and the resulting 38,000 miles per hour represents the absolute peak of human propulsive achievement. Across nearly 5 decades of spaceflight, the resulting velocity of approximately 38,000 miles per hour represents the fastest sustained speed ever achieved by a human-made object. At this velocity, Voyager 1 covers approximately 912,000 miles every 24 hours, roughly 3.8 times the distance from Earth to the Moon every single day. Without stopping, at this speed, the absolute peak of human propulsive achievement, the fastest we have ever managed to send anything reaching Proxima Centauri, would require approximately 75,000 years, not 73,000 days, not 73,000 months, 73,000 years. Anatomically modern humans have existed as a species for approximately 300,000 years. Recorded human history spans approximately 5,000 years. Agriculture was developed approximately 12,000 years ago. The earliest known permanent human settlements date to approximately 10,000 years ago. The time required for Voyager 1 to reach the nearest star if it were travelling in that direction, which it is not, is approximately 15 times the entire span of recorded human civilization, and roughly 1/4 of the entire duration of our species' existence on Earth. To frame this from the other direction, when light left Proxima Centauri this morning and began its 4.24 light-year journey toward Earth, that light will arrive here in 4 years and approximately 3 months. If a human civilization sent a radio message to Proxima Centauri today and waited for a response, the minimum possible round-trip communication time, assuming an immediate reply, would be approximately 8.5 years. Any meaningful exchange of information with the nearest stellar system would unfold on timescales measured in human generations rather than human lifetimes, even at the absolute physical speed limit of the universe. A scale model makes the spatial relationship concrete in a way that raw numbers cannot. If the distance from the Sun to the Earth, 1 astronomical unit, approximately 93 million miles, is represented as 1 single millimeter, then on this scale, the solar system takes on the following proportions. Neptune orbits at 30 millimeters from the Sun, 3 centimeters, fitting comfortably across 2 fingers. The termination shock at approximately 90 astronomical units sits at 90 millimeters, roughly the width of a hand. The heliopause, at approximately 120 astronomical units, sits at 120 millimeters, about the length of a standard ruler from its edge to the 12 centimeter mark. And Proxima Centauri, the nearest star, sits at approximately 268,000 millimeters from the Sun. On this scale, 268 meters, roughly the height of the Eiffel Tower. On this scale, the entire solar system, out to the heliopause, fits within a region the size of a dinner plate. The nearest star is 268 meters away, nearly 3 football fields. The interstellar medium fills the space between. And that space, those 6 meters on the scale model representing 25 trillion actual miles, contains essentially nothing but the local interstellar clouds, 0.3 of an atom per cubic centimeter, the weak interstellar magnetic field, the continuous galactic cosmic ray flux, and the occasional interstellar dust grain. 6 meters of almost perfect vacuum on a scale where the Sun is a single millimeter and the Earth is roughly 1/100th of a millimeter. But Proxima Centauri is not the only nearby star. The local stellar neighborhood, the volume of space within approximately 15 light-years of the Sun, contains a specific, mapped population of stellar systems whose properties are known with precision from decades of observational work. Understanding this neighborhood is not merely a cataloging exercise. The properties of these nearby stars define the particle and radiation environment of the interstellar medium between them, and those properties reveal something important about what the local interstellar environment is actually like, across the full distance to the nearest stellar systems. Proxima Centauri is a red dwarf of spectral type M, 5.5 among the coolest, dimmest, smallest stars, classified as genuine hydrogen-burning main sequence stars. Its surface temperature is approximately 3040 Kelvin, roughly half the temperature of the Sun's photosphere. Its luminosity is approximately 0.17% of the Sun's output. It produces roughly 600 times less light than the Sun. If Proxima Centauri replaced the Sun at the center of our solar system, Earth would receive so little energy that the planet's surface would freeze solid within decades. Proxima Centauri's mass is approximately 12% of the Sun's mass, small enough that if it were significantly less massive, the pressure and temperature at its core would be insufficient to sustain hydrogen fusion, and it would be a brown dwarf rather than a star. Despite its feeble luminosity, Proxima Centauri is magnetically violent. It is a flare star, a category of red dwarf that produces sudden, intense releases of magnetic energy in the form of ultraviolet and X-ray flares that can briefly increase its total luminosity by factors of hundreds to thousands. In March of 2016, a superflare from Proxima Centauri temporarily increased its ultraviolet output by a factor of approximately 1,000 relative to its quiescent level, with the flare event lasting approximately 2 minutes at peak intensity. For any planetary surface in the system, the ultraviolet dose rate during such an event would be orders of magnitude above anything in the solar system's habitable zone on Earth's worst day of solar activity. Proxima Centauri b, the confirmed terrestrial mass planet, detected in 2016 through the radial velocity technique, which measures the tiny wobble a planet's gravity induces in its host. Star's motion orbits its star at approximately 0.048 astronomical units. For comparison, Mercury orbits the Sun at approximately 0.39 astronomical units. Proxima Centauri b is more than 8 times closer to its star than Mercury is to the Sun. It orbits once every 11.2 days. At this distance, it receives approximately 65% of the energy per unit area that Earth receives from the Sun, placing it within the nominal habitable zone defined by the stellar energy flux alone. But the habitable zone definition accounts only for the stellar luminosity's capacity to maintain liquid water at the surface. It says nothing about flare radiation, stellar wind particle flux, or the magnetic environment. The stellar wind from Proxima Centauri, the equivalent of our solar system's solar wind, is estimated to be significantly more intense than the Sun's solar wind in terms of particle flux per unit area at the planet's orbital distance, despite the star's low luminosity. The close orbital distance of Proxima Centauri b means it is immersed in a stellar wind that is substantially denser at its location than the solar wind is at Earth's orbit, even though the star itself is much less luminous. The resulting astrosphere, the Proxima Centauri equivalent of our heliosphere, may be smaller and weaker than ours relative to the surrounding interstellar medium, and the planet itself, orbiting so close to the star within this compressed astrosphere, faces a particle radiation environment that may strip atmosphere from its surface over geological timescales. Whether Proxima Centauri b retains an atmosphere, whether it has liquid water, whether it has a magnetic field strong enough to deflect its star's particle wind, whether it is tidally locked, rotating synchronously with its orbit, so that one hemisphere permanently faces the star while the other is in eternal darkness, these questions remain entirely open. No instrument currently in operation can characterize the planet's atmosphere or surface. The nearest planetary system is simultaneously accessible to detection and inaccessible to characterization with our current capabilities. We know it exists. We know almost nothing else. The two brighter members of the Alpha Centauri system, Alpha Centauri A and Alpha Centauri b, orbit each other as a gravitationally bound binary pair, their separation varying between approximately 11 astronomical units at closest approach and approximately 36 astronomical units at their widest. completing one mutual orbit approximately every 79.9 years. Completing one mutual orbit approximately every 79.9 years. Alpha Centauri A is a Type G2 main sequence star, essentially a solar twin, slightly larger and more luminous than the Sun, with a surface temperature of approximately 5,790 Kelvin and a luminosity approximately 1.5 times solar. Alpha Centauri B is a Type K1 main sequence star, smaller and cooler than both the Sun and Alpha Centauri A, with a surface temperature of approximately 5,290 Kelvin and a luminosity approximately half of solar. The proximity and brightness of these two stars have made them targets for exoplanet searches. Though confirmed planets in the Alpha Centauri AB system have proved elusive, a candidate planet detection from 2012 was subsequently retracted, and the observational challenge of detecting planets around stars in a close binary system remains significant. Moving outward through the local stellar neighborhood, the population continues to be dominated by red dwarfs. Barnard's star, at approximately 5.96 light-years, the fourth nearest star system, is a Type M4 red dwarf, notable for its extraordinary proper motion across the sky. It shifts its angular position relative to background stars by approximately 10.3 arc-seconds per year, the fastest proper motion of any known star. This rapid motion reflects its relatively close distance combined with a significant velocity relative to the Sun. A candidate super-Earth in a potentially habitable orbit around Barnard's star was announced in 2018, but has not been confirmed with high confidence. Wolf 359, at approximately 7.78 light-years, is a Type M6 red dwarf of such extreme magnetic activity that it was the source of one of the most energetically intense stellar flares ever directly recorded. The census of stars within 15 light-years of the Sun contains approximately 56 stellar systems, hosting approximately 67 individual stars and brown dwarfs. Of these, approximately 45 are red dwarfs of Type M, 5 are orange dwarfs of Type K, 2, the Sun and Alpha Centauri A, are yellow dwarfs of Type G. 1 Sirius A, at approximately 8.6 light-years, is a white main sequence star of Type A, approximately twice the solar mass and approximately 25 times the solar luminosity. Sirius A's binary companion, Sirius B, is a white dwarf, the remnant core of a star that exhausted its fuel and shed its outer layers, leaving behind a hot, dense, cooling cinder approximately equal to Earth in size but to the Sun in mass. The statistical implication of this local census applies globally. Red dwarfs constitute approximately 70% of all stars in the Milky Way, the brilliant, luminous stars that dominate the night sky. Sirius, Vega, Rigel, Betelgeuse are spectacularly rare exceptions. The galaxy is overwhelmingly populated by dim, long-lived, magnetically volatile red dwarfs that produce so little light they are essentially invisible to the naked eye at even the modest distances of the nearest stellar systems. The nearest star bright enough to see without optical aid under dark sky conditions from Earth is Alpha Centauri A and B combined, which appear as a single point of light at magnitude -0.3 in the southern sky. Proxima Centauri, only slightly farther away, has a magnitude of approximately 11, roughly 100 times too faint to detect with the unaided eye. For the interstellar medium between the solar system and these nearby stars, the relevant physical context is that of the local interstellar cloud, as characterized in the previous section, approximately 0.3 hydrogen atoms per cubic centimeter, temperatures of 6,000 to 8,000 Kelvin, weak interstellar magnetic field of approximately 0.3 to 0.5 nanotesla, full galactic cosmic ray flux. This environment extends approximately continuously from just beyond the heliopause to the astrospheres of the nearest stellar systems. There is no protective structure, no transition to a more benign environment, no region where the conditions become less hostile to an unprotected spacecraft or organism. The interstellar medium between here and Proxima Centauri is the same interstellar medium that the Voyager spacecraft are currently sampling at 160 astronomical units, just extending for an additional 4 light-years. Approximately 269,000 additional astronomical units. In every direction, serious proposals for reaching the nearest stars within human-relevant timescales exist and deserve honest examination. The Breakthrough Starshot initiative, announced in April 2016 by a group including physicist Stephen Hawking and entrepreneur Yuri Milner, with backing of $100 million for research and development, proposes accelerating gram-scale spacecraft to approximately 20% of the speed of light using a ground-based phased laser array. At 20% of light speed, approximately 134 million miles per hour, such a spacecraft would reach the Alpha Centauri system in approximately 20 to 22 years. The concept is grounded in known physics. Laser propulsion and light sails have been demonstrated at small scales, and there is no fundamental physical law that prevents the approach from working. The engineering obstacles, however, are substantial, and none have been resolved as of current technology. The proposed laser array would need to deliver approximately 100 gigawatts of focused, coherent laser power to the sail, a power level roughly equivalent to the total electrical generating capacity of the United Kingdom, for a period of approximately 10 minutes during the acceleration phase, maintaining the beam's diffraction-limited focus on a sail measuring perhaps several meters across, over an acceleration distance of roughly 10 million kilometers, requires adaptive optics systems of a precision not yet demonstrated at any comparable scale. The sail material must survive the initial laser pulse without vaporizing, distorting, or tearing a pulse that delivers more energy per unit area than any known material has survived intact. And the gram-scale payload, carrying cameras, spectrometers, and a laser communication system capable of transmitting data across 4 light-years, must be designed within mass constraints that make every component a challenge of miniaturization beyond current capability. Even if all of these obstacles were resolved, the interstellar medium itself imposes constraints on the mission. At that velocity, the spacecraft's collision cross-section with interstellar dust grains becomes significant in a way that is entirely negligible at Voyager speeds. An interstellar dust grain of approximately 1/10 of a micrometer diameter, typical of the grain size distribution in the local interstellar cloud, carries kinetic energy in the spacecraft's rest frame of approximately 1/10 of a millijoule at 20% of light speed. For a gram-scale sail material with a real density of grams per square meter, the cumulative erosion from thousands of such impacts over a 4 light-year transit would degrade the sail's reflectivity and potentially compromise its structural integrity. Larger, rarer grains approaching a micrometer in diameter could carry enough kinetic energy in a single impact to punch through the sail or destroy the payload entirely. Designing a sail that is simultaneously light enough to be accelerated efficiently, large enough to intercept the laser beam effectively, and robust enough to survive thousands of dust grain impacts at relativistic velocities is a design problem for which no current material solution exists. The galactic cosmic ray environment at 20% of light speed presents an additional complication. At relativistic velocities, the spacecraft's electronics are exposed to galactic cosmic rays arriving from the forward hemisphere at higher effective energies due to relativistic beaming, the same effect that causes rain to appear to fall at an angle toward you when you run through it. The single event effect rate in the spacecraft's electronics increases at relativistic velocities compared to stationary exposure, further stressing the already challenging requirement for radiation-hardened computing systems with the performance and miniaturization needed for a gram-scale payload. These are not objections intended to dismiss the concept. They are characterizations of real physical constraints imposed by the interstellar medium itself. The medium does not merely need to be traversed, it actively resists traversal at the velocities required to make the journey meaningful. Every property of the interstellar environment between here and Proxima Centauri, the dust density, the cosmic ray flux, the magnetic field becomes a mission design constraint for any spacecraft attempting to cross it at speeds that would make the crossing worth attempting. For missions at Voyager speeds, the only speeds currently demonstrated for interstellar transit, the constraints are different in character but no less definitive. 73,000 years to the nearest star. The entire span of human civilization has lasted approximately 5,000 years. No continuous human institution, no government, no religion, no scientific organization has maintained operational continuity for even 1,000 years in their current recognizable form. The idea of maintaining a spacecraft mission, maintaining the knowledge base to interpret its data, maintaining the communication infrastructure to receive its transmissions, and maintaining the organizational continuity to care what it finds for 73,000 years is not an engineering problem. It is a civilizational one, of a kind no civilization in recorded history has come close to demonstrating the capacity to solve. And yet the Voyager spacecraft are there, beyond the heliopause, in the interstellar medium, transmitting data from a place that no prior human technology had reached. Built in the 1970s with technology that any modern smartphone surpasses in computational power by many orders of magnitude, designed for a mission expected to last approximately 4 years, now in their 48th year of operation, they are still functioning, still measuring, still returning data from an environment whose properties we would not otherwise know. This is the context in which the conclusion of this story belongs. Not in despair at what we cannot yet do, but in clarity about what the measurements actually reveal. The solar system is not the normal condition of space. It is an exception. The Sun, by continuously outputting the solar wind and maintaining the heliosphere, has spent 4.5 billion years creating and defending a region of modified space, approximately 240 astronomical units, across roughly 0.004 light-years in diameter, within which the galactic cosmic ray flux is meaningfully reduced by the heliospheric magnetic field, the interstellar plasma is excluded, the magnetic environment is organized by stellar rather than galactic processes, and the conditions are, in aggregate, substantially less hostile to complex chemistry and biology than the surrounding interstellar medium. This exception is not stable in the long term. The Sun will eventually evolve off the main sequence. The solar wind will change dramatically, and the heliosphere will no longer maintain its current form, but for the approximately 5 billion remaining years of the Sun's main sequence lifetime, the heliosphere will continue to hold. The nearest analogue to this protected environment is the astrosphere of Proxima Centauri, 4.24 light-years away across the full hostility of the local interstellar cloud. In between, there is no shelter, no reduction in cosmic ray flux, no stellar magnetic protection, no warm plasma environment. Only the interstellar medium as it actually is: diffuse, cold, magnetically threaded, radiation-saturated, and indifferent to the survival of anything passing through it. The galaxy contains somewhere between 200 billion and 400 billion stars. Each of those stars maintains its own version of the protective bubble our Sun maintains for us. But those bubbles are separated from each other by distances that, even at the speed of light, require years to cross, and at any speed currently achievable by human technology require tens of thousands to millions of years. The galaxy is not a connected environment. It is a collection of isolated stellar islands, each surrounded by its own modest sphere of modified space, each separated from its neighbours by vastly larger regions of unmodified interstellar medium. Our heliosphere, at approximately 240 astronomical units across, represents approximately 0.09% of the distance between the Sun and Proxima Centauri. If the distance to the nearest star were represented as the length of a standard football field, 100 yards, the diameter of our entire heliosphere, the full extent of the Sun's protective domain would represent approximately 3 inches, a small fraction of a single human hair's width on a football field. That is the fraction of interstellar space that our Sun has successfully modified into a habitable environment. Everything that has ever lived on Earth, every organism in the fossil record, every bacterium in the deep ocean, every human being who ever existed has lived within that hair's width fraction of the space between here and the nearest star. 4.5 billion years of biological evolution, the entire history of complex life on this planet, the entire span of human civilization, every scientific discovery ever made, every piece of music ever composed, every war ever fought, all of it occurred within a bubble so small that it occupies a negligible fraction of the distance to our nearest stellar neighbour. And the moment anything crosses the heliopause, the moment any spacecraft, any probe, any future human mission exits that protective domain, it enters an environment that has never been shaped by the sun, that has never been modified to be less hostile, that does not care whether the objects passing through it survive the crossing. The interstellar medium does not become more hospitable farther out. It does not thin into something less threatening. It simply continues at the same density, the same radiation level, the same magnetic character, all the way to the next star's astrosphere, across 25 trillion miles of measured, quantified, instrument-confirmed hostility. Leaving the solar system is not travelling farther into space. Every spacecraft launched by humanity has travelled into space. The Apollo missions travelled into space. The Mars rovers operate in space. The Voyager spacecraft travelled through space for decades before they reached the heliopause. Travelling into space, within the heliosphere, means travelling through an environment that is unusual by galactic standards. A stellar wind-filled, magnetically organised, partially shielded from cosmic radiation bubble that represents the sun's continuous physical output. Leaving the solar system means exiting that environment entirely and entering the baseline condition of the interstellar medium, the condition that prevails across the vast majority of the galaxy's volume. In the space between the stellar islands, where no star's wind reaches and no star's magnetic field provides any protection, and the galactic cosmic ray background arrives at its full unmodulated intensity. It means crossing from one physical regime into a fundamentally different one, at a boundary that both Voyager spacecraft have now confirmed is sharp, measurable, and real. The heliosphere is small. By galactic standards, it is almost unimaginably small, a microscopic sphere of modified space embedded in a galaxy 100,000 light-years across. But from the perspective of every living thing that has ever existed on Earth, it is everything. It is the entire physical domain within which life emerged, evolved, and developed the capacity to measure the boundary of its own home. We now know where that boundary sits. We know what it is made of. We know what the instruments measure when they cross it. And we know what waits on the other side, not as speculation, not as inference from theory, but as direct measurement from the two most distant objects humanity has ever made. The solar system is protected, profoundly, specifically, physically protected by a star that has been spending its own mass at a rate of 1 million tons per second for 4.5 billion years, holding the galaxy at arm's length. Beyond the heliopause, the galaxy stops being held back. It presses in from all directions, as it always has, as it will for billions of years to come, cold, ancient, radiation-bathed, and vast beyond any scale that feels real when you are standing on one small planet inside the exception. The Voyager spacecraft are in it now. They crossed the boundary and kept transmitting. And what they found confirmed what the physics predicted. That the sun's domain ends sharply, that the interstellar medium begins immediately, and that the distance between what we are and where the nearest star sits is not a journey, it is an ocean. And we have, so far, managed to wade in only up to our ankles.